So let's consider work in one-dimensional motion. So for example, even though this is really 2D, it's really 1D, right? So this is a force, right, F, pushing on a box, say. And this is a friction force, F sub K, or something like that. And then there's a normal force, right? And there's a force of gravity. And if the box is sliding along, these two guys add up to 0, right? And then, so F net is just equal to F minus Fk in the x direction. I don't have to worry about these guys because I know it's not accelerating that way, and so I know these guys must cancel because it's on a horizontal surface and all that stuff. And so for this system, I can say, look, the net work done is just equal to F net times cosine theta times the distance, right? And if I wanted to, I can call these vectors. But F net is just along the x-axis, and that's the direction this guy moves. I'll just make that clear here, right? And so that means this is just F net times cosine of 0 times d, but cosine of 0 is just 1, and so that's F net times the distance is the net work done. In one dimension, you're either pushing in the direction of the distance or you're pushing opposite the direction of the distance, either one, right? And so we can look at this thing and say, well, from Newton's second law, we already know that the net force is equal to the mass times the acceleration, right? Again, this is all in the x direction, so I don't have to worry about vectors. And so that means that W net, which is F net times distance, is equal to mass times acceleration times distance. And now I want you to remember this formula for from chapter 2, and that's, so I'll say recall, v squared is equal to v naught squared plus 2a times x minus x naught, right? In that problem, this is the distance, right? And so I could write this as v squared is equal to v naught squared plus 2a times d, or I could say a times d is equal to v squared minus v naught squared over 2. You see what I did there? I moved this to the other side with a minus sign. That gives me a 2ad, and I divided both sides by 2, or it's equal to v squared over 2 minus v naught squared over 2. And so I can take these two guys here, and I could substitute them in for those two guys, and I get the net work is equal to the mass times v squared over 2 minus v naught squared over 2. You with me? I just substituted those in there, and that's my net work. Or it's equal to 1/2 mv squared minus 1/2 m v naught squared. That's the net work done. So this is my final velocity. This is 1/2 m times my final velocity squared minus 1/2 m times my initial velocity squared is the work done, right? One half mv squared is called the kinetic energy. It's the energy due to motion. And so what I would say is this. So W net is the net work done on the system is the change in kinetic energy of the system. It's called the work energy theorem. Sometimes it's called the work kinetic energy theorem. Sometimes. It's usually just called the work energy theorem. And so the net work done on a system is the change in kinetic energy of the system. If the system ends up with a positive change in kinetic energy, positive work was done. In other words, if the thing ends up moving faster than it started, then positive work was done. If the thing ends up moving slower than it started, then negative work was done. In other words, the effect of the work was to slow the object down. If negative work is being done, energy is being pulled out of the system. If the kinetic energy increases, if the object speeds up, then positive work is being done on the system. So in this problem, you push a 30 kilogram box with 120 Newton force through a distance of 0.8 meters. So it goes from here to here, it moves 0.8 meters against a 5 Newton friction force. See the drawing. So A, what is the net force? Right? Well, you would also have a force of gravity, and you'd also have a normal force. But these are equal and opposite, so they cancel out. And so it's just F minus Fk, which is 120 newtons, minus 5 newtons, which is 115 newtons. Right? B, what is the net work done, right? Well, the net work is equal to the net force times the cosine of the angle between them times the distance, right? I don't have to really worry about vectors here because they're in the same direction, right? And so the net work is equal to 115 newtons. The net force times the distance it moves, which is 0.8. Cosine of theta, theta is 0 in this case because the force is going that way and the distance is going that way. And so I could say times the cosine of 0 degrees times 0.8 meters, right, which is about 92 joules, something like that. So we can ask, what's the work done by the force F and Fk, right? The work done by F is equal to the magnitude of F times the cosine of theta times the magnitude of D, right? And that's 120 newtons times, again, it's pushing that way and the object's going that way, and so its cosine is 0 degrees times 0.8 meters, which is 96 newtons, right? Because 0.8 times 120 is 96, and cosine of 0 is 1, right? And similarly, I can say, look, the work done by the force of kinetic friction is the magnitude of that force times the cosine of the angle between the force and the distance times the distance. And so this is 5 newtons. That's the magnitude of this. Now I have to be careful because the friction force is pointing that way, but the object is moving that way, and so this is cosine of 180 degrees times 0.8 meters. Sorry, this is Newton meters up here, which is 96 joules. Sorry about that. And so this is 5 newtons times 0.8 times the cosine of 180, which is -1. This is -4 newtons. Right? And so if you look at this, the net work done, not newtons, joules. If I calculate the works done individually and add them up, I get the same thing as the net work done. I could just take it, calculate the work done by each individual force, add them up, and gotten the net work. So here I subtracted the forces and calculated based on the net force. Here I just calculated the work done by each force individually and added those up and calculated the net work. I could say W net equals WF plus WFK, if you want to call it that. I'd still get the same answer. So next, let's ask, assuming the box started from rest, how fast is it going once I've pushed it to that point, right? And so here we say, look, well, the net work done, which we already calculated, is the change in kinetic energy, right? Which is 1/2 mv squared minus 1/2 mv initial squared. And remember, I was putting a naught here. Remember, assuming it started from rest, it's got no initial kinetic energy, right? It's got no energy of motion if it starts from rest. And so W net is just equal to 1/2 mv final squared. I'll get there. They're asking us for v, the speed, and so if I solve for v squared, that's equal to 2 W net over m, or v is equal to the square root of 2 times the net work done over m, which is equal to the square root of 2 times 92 joules divided by 30 kilograms. I get about 2.5 meters per second, roughly speaking. Let me just check that. Close enough. So we're going to talk a little bit about a quantity we call potential energy. Potential energy is kind of stored energy. We talked about kinetic energy. Kinetic energy, which is defined as 1/2 mv squared, is the energy associated with motion. Potential energy is energy that's somehow stored. I can store energy in a spring by stretching it like this, and then I can attach something to this hook and release it, and it'll shoot that thing off somewhere. Or I can just store energy by raising something up in a gravitational field, and then I can drop it and have it do work by smashing something, say. So potential energy is energy that's stored. A stretched spring has potential energy. A lifted mass has potential energy. And so I'm going to sort of quantify that for you here. Let's say I have a box, right? Here's my box. We'll call this my box. And I raise it to a height h, right? That's what I'm doing here. I'm raising the box. Well, how much force does it take me to lift a box? I have to actually exert a force that balances its weight, or maybe a tiny bit more than that. But we'll just say I have to pull up as hard as gravity pulls down, and once I get it going, it'll just keep going. And so, so the force I have to apply equals the force of gravity, which is the weight. And so when I raise the box to a height h, the work done by me on the box is force times cosine theta times h, where theta is the angle between the force and the distance, right? The force and the h. But those are in the same direction, right? The box is going up and the force is going up. And so this is just 1, because theta is 0, cosine theta is it's cosine 0, and that's 1. And so that's just the force times the height, but we already said the force was mg. And so the work done by me to lift the box to a height h is mgh. It's just the weight times the height. Notice that at the same time, when I lift the box against gravity, gravity is pulling the other way. And so while I'm doing positive work, gravity is doing negative work. Here's the work gravity does. Work by gravity is force of gravity times cosine theta times the height, because that's the distance it goes, that's the force. The angle, however, is this angle, which is 180 degrees now for the angle between gravity and the distance the object is going. Cosine of 180 degrees is -1, and so I get mgh times -1, or minus mgh. Notice that while the box is being lifted, I'm doing positive mgh of work lifting it. Gravity is doing negative mgh. The net work is 0. And that should make sense, because we already said that the net work is equal to the change in kinetic energy. But if I just raise the box up slowly, its kinetic energy does not change. And so this side is 0. And so as I'm doing positive work, gravity is doing the same amount of negative work. What's interesting about that is that at any point, I can have gravity do positive mgh of work just by letting the box go. If I release the box right here, I'm exerting no force on it. Gravity is exerting mg. The box will fall that distance, and so mg will be acting down. The box will be going down, and so the work done by gravity would be mass times force times cosine theta times the distance. And since the force and the distance are in the same direction, cosine theta is 0. And I would get a positive mgh of work here. And so by lifting a box against gravity, having gravity do negative work, I'm actually just using that energy as stored energy, like stretching the spring. And so what we do is, instead of saying W by me plus W by gravity equals the change in kinetic energy, we say W by me equals minus the work done by gravity plus the change in kinetic energy. So instead of writing, our work done is the sum of all the works that are done, and that's equal to the change in kinetic energy, we're moving the stuff that gravity does over to the energy side of the equation instead of the work side of the equation. And this we're going to call the potential energy. Because when gravity is doing negative work, when the object is being raised, even though gravity is doing negative work, the potential energy is increasing, because the higher it gets, the more positive work I can get out of it. And so we say where the potential energy due to gravity is mass times gravity times height. Again, it was minus mgh on this side. That makes it plus mgh on this side. And so I have a plus mgh here. And so, this is the form. So I can say, look, work by me equals potential energy due to gravity final minus potential energy due to gravity initial plus KE final minus KE initial. Write it that way. Or as I said, change in potential energy due to gravity plus change in kinetic energy due to gravity, where the potential energy is defined this way and the kinetic energy, not kinetic energy due to gravity, just kinetic energy. So let me do an example. So a box is raised to 2.5 meters, a 20 kilogram box. Determine the work done raising the box. So this is the force, I'll say, by the lifting force, right? And so the work done by the force is force times cosine theta times the height, right? That's, I grab the box and I slowly lift it, and I'm exerting a force equal to its weight, and I'm raising it at height h, and the angle between those two, since I'm lifting it and it's going this height, is 0. And so this is mass times gravity times height, or 20 kilograms times 10 meters per second squared times 2.5 meters, right? And it's 20 times 10 is 200 times 2.5 is 500. 500 kilogram meters squared over second squared, that's 500 joules. So the work done by gravity is equal to the force of gravity times cosine theta times the height, right? And that's just mg times cosine of 180 degrees, because gravity is being pushing down, but the object is going up, right? Gravity is pushing down on the box, and the box is moving up. And so times height, which is 20 kilograms times 10 meters per second squared times minus 1 times 2.5 meters, that should be a times, which is minus 500 joules, right? So while I'm doing positive work, gravity is doing the exact same amount of negative work as I raise this object, right? And so C is so the net work is just all the forces that are acting on it. How much do they do? Well, the force by the work done by the force, which is really by me, but it's by the force I exert on it, is 500 joules, plus the negative 500 joules that gravity is doing is 0 joules. And when I raise it up, it comes to a stop. You know, I raise it slowly, and so it gains no real kinetic energy in that process, and so the net work is 0. And then I can say D right? The potential energy due to gravity is mg times the height, right? And that h here is how high it is, and so PE due to gravity final is equal to mg times h. PE due to gravity initial is equal to mg times 0, because that's when it's on the ground. And so PE due to gravity, the change in potential energy due to gravity, which is what they're asking here, is PE gravity final minus PE due to gravity initial, which is mgh minus 0, because mg times 0 is that. And so it's 20 kilograms times 10 meters per second squared times 2.5 meters, which is 500 joules. And so notice when gravity is doing negative 500 joules of work here, the object is gaining 500 joules of potential energy. As the more negative work gravity does, right, as I lift this object up, as I raise an object, the more negative work gravity does, gravity's pushing this way, the object's going this way, the more energy I can get back out when I release it. And so as gravity does more negative work, the potential energy increases. And so this is our formula for potential energy, where h is how high it is. I've got another part, so that was D. But if I save the box, so if the object is dropped from 2.5 meters, and so now I'm not talking about lifting the box anymore, I'm saying, look, this is the initial situation, and this is the final situation. It's right before it hits, right? And so I can say, look, V initial is equal to 0, and I can say H naught is equal to 2.5 meters. H is equal to 0 meters, right? That's right before it hits the ground. V final, so I'm going to call this guy V naught, and V is equal to question mark. Right? All I've done is I've held the box up here, and I've released it. Right? And so I can say, look, the work is equal to the change in potential energy plus the change in kinetic energy. Well, I don't have to worry about the work due to gravity, because that's in here. This is all other forces besides gravity, all what we call non-conservative forces like me or anything else. But there are no forces doing work over here, because all I do is release it. And so this guy is 0 is equal to the change in potential energy plus the change in kinetic energy. Right? But that means that 0 is equal to PE final minus PE initial plus KE final minus KE initial. Right? The final potential energy minus the initial potential energy equals the final kinetic energy minus the initial kinetic energy. So you should be able to figure out right away that this guy is 0, because 1/2 m V naught squared is 0, because V naught is 0 if I dropped it from rest, if I was holding it and let it go. Secondly, potential energy is mgh, and if my height is 0 here, then this term is 0. And so what this says, what I'm left with is 0 is equal to minus PE initial plus KE final, or KE final equals PE initial. But this just says that 1/2 m V squared is equal to mg h naught. Right? I can cancel the m's, and I get V squared is equal to 2g h naught, or v is equal to the square root of 2g h naught, which is equal to the square root of 2 times 10 meters per second squared times 2.5 meters, which is equal to the square root of 50 meters squared over second squared. That's what my v is. And if I just write it over here, v is equal to about 7.1 meters per second. And so let me just say a few things about this on the next sheet.